Okay, so today we're going to be looking at osmolarity and how we can use this concept of osmolarity to answer questions when they're proposed to us. So we've got this question, a 0.89% weight to volume sodium chloride solution. So I'm going to pull out that information as we read it. And it is weight to volume. And it says that this solution is a physiological saline. Okay, it's what's considered the concentration that blood happens to be. Okay. What is the osmolarity of this solution? And we're given the molar mass of sodium chloride. We should be able to calculate this, but it'll save us a little bit of time having it in the problem. All right. So, what we want to know is, what is the osmolarity? Well, osmolarity, the first thing I'm going to think of is, okay, I know the formula for osmolarity, right? We have to have this memorized. It's molarity times I. Well, sodium chloride, the easiest one to get here is I, right? So the I of sodium chloride is going to be what? Sodium chloride, when it goes into water, goes to sodium plus, chloride minus. So we're going to have two particles from this one particle. So our I is 2. Okay. Next thing we need for that osmolarity is our molarity. Okay. We don't have that, but we have a concentration. If we have a concentration, we should be able to convert it to another concentration. So we're going to change our percent concentration into molarity. This is a percent concentration, so anytime we have any type of concentration, we're going to get into units we can actually cancel out. So this is going to equal 0.89, weight is on top, so that's grams of our solute, in this case it's the sodium chloride, per 100 grams of our solution. Okay. Now we can go ahead and use this. Now, normally we would say, it's 100 milliliters. This is volume, so good check there. Let's make sure we get the right units for what we're talking about. This is weight on top, which is grams, volume on the bottom, which is milliliters. So now we've got our conversion factor correct. Normally we would say we start with a thing that's not the conversion factor, but what we're doing is we're going to change this from one concentration to another concentration. So we're keeping it as a conversion factor, we're just changing it to a different conversion factor. So that's the one that we're going to start off with. So let's go ahead and write this down. This is the sodium chloride per 100 milliliters of solution. So what we need is molarity. Write it in a different color so it stands out here. We need molarity, capital M. And what is that? And we change it to units that we can cancel out. Well, it's moles of solute, in this case the sodium chloride, per liter of solution. Okay. So if we can convert that grams to moles and we can convert the milliliters to liters, we've got it. And yes, we can do both of those conversions. So, grams to moles. What conversion factor do we use to convert grams to moles? Molar mass. Exactly. We've got grams and we've got moles here, so we can definitely use that as a conversion. So, grams are in the top, so where do they have to be to cancel out? They have to be in the bottom. So we're going to put the grams of our conversion factor down there in the bottom. It's 58.5 grams of the sodium chloride per 1 mole of the sodium chloride. So it's the molar mass of sodium chloride. Okay. Grams will cancel out with grams. Now the only thing in the numerator is moles, and that's what we want. So we're on the right track there. Now we have to get the denominator converted over. Milliliters, we have to get it to liters. Not a problem, we can do that because we know our metric conversion factors. Milliliters is in the bottom, so where do they have to be to cancel out? They have to be in the top, exactly. So we've got 1 liter, and it is 1,000 of the little guys. Okay. Milliliters cancels out with milliliters, and we'll end up, this is of solution, and of solution, we'll end up with moles per liter. So we'll do this calculation. Our units will be moles per liter, and that's the solute to solution. Let's go ahead and grab our calculators, and I'll do this with you. 0.89 times 1 times 1,000 divided by 100 divided by 58.5 divided by 1, and we should get 0.15 moles per liter. Moles per liter is molarity, so this is 0.15 molar. Okay. Now we have that number that we needed for our osmolarity. Okay. Now it's a matter of calculating our final number. We were asked for the osmolarity, so that's what we're going to do. It's molarity times I. Our molarity was 0.15 molar. Our I, we said, was 2. So we get 0.30 osmolar. Now keep in mind, I'm keeping my significant figures here. I make sure that there's a big enough space there that I don't think that that O is another one of those digits. So just make sure that you can differentiate those two so I know where the number is and where your units start. So here's our final answer on the osmolarity. So physiological saline is 0.30 osmolar. And generally, if you work enough these problems, you'll see that the problems will either give you 0.30 or 0.29 osmolar as your osmolarity for physiological saline. Use whichever one you're given. Okay. Here we calculated it as 0.30. So we can take any concentration. It doesn't have to be just molarity. We can take any concentration, we can convert it to molarity, and we can get our osmolarity of that solution. Okay. Now let's go on and talk about how we compare solutions that have different osmolarities. And here we've got, say we've got a solution and we have a red blood cell inside. The red blood cell, we just calculated physiological osmolarity for our person is 0.30 osmolar. So inside that red blood cell is going to be 0.30 osmolar. Okay, physiological saline, physiological condition. Now, if we have a solution or two solutions that have the same osmolarity, they are said to be isotonic. Iso means the same. So an isotonic solution are two solutions with the same osmolarity. Now we're going to look at how it affects the red blood cell. So when we're saying it's in an isotonic solution, it means that this solution has the same osmolarity as our red blood cell. So this solution on the outside of the red blood cell is 0.30 osmolar. Inside the red blood cell is 0.30 osmolar. Okay. They are the same. In that case, the red blood cell is nice and happy. So we've got a happy red blood cell, and nothing changes. Okay, nothing changes. Let's look at what happens when we've got a different type of solution. Here we're going to look at a hypertonic solution. Okay. Now hyper means too much. Okay. So the solution is actually going to have a higher osmolarity than the red blood cell. So it could be anything. It could be, let's say, a 0.5 osmolar solution. It could be a 3 osmolar solution. Just as long as it's higher than 0.30, it is hypertonic. And in this case, what's going to happen is we have to think back to our osmosis. Okay? The water always flows in the direction to dilute out the higher concentration. So it always flows towards the higher concentration. So what's going to happen here is the water inside of this cell is going to come flooding out. What's going to happen to the red blood cell when that occurs? Well, it's going to shrivel up. Okay? It'll shrivel up and it'll get little peaks on it because it's all shrivelly. And in your slides, there's a much better picture of this. There's an actual red blood cell that's doing this. This is called crenation. With it shriveling up because all of the water came flooding out. Remember that water is going to try to make these concentrations even inside the cell and outside the cell. So if you've got more or a higher osmolarity outside the cell, the water is going to go towards that direction. Let's look at the other condition. Here we've got a hypotonic solution. Hypo is a prefix that means too little. If we remember that hypo means too little, that means that the solution that this guy's in has got a lower osmolarity. Let's say it's 0.15 osmolar. Okay. In that case, the water's going to move so that it dilutes out the higher concentration. So which direction is the water going to go? It's going to flood into the cells. If it floods into the cell, what's going to happen to the red blood cell? Well, it's going to swell, right? The first thing it'll do is swell, and if it continues to swell and swell and swell, it will actually burst. And it'll cause the cell to lyse. So here we've got the red blood cell will swell, and eventually it will lyse. So we can see that having the right osmolarity for a particular situation is very, very important. What's going to happen if you put a red blood cell into pure water? Say you're dehydrated and they want to give you an IV and they put pure water in it. What's going to happen to all your little blood cells? Well, pure water has a lower osmolarity than your red blood cells. This situation is going to happen. Water's going to flood in and your cells are going to lyse. That's not a healthy condition to be in. So you don't want them to give you pure water when you're dehydrated in the hospital. And that's why when you're in the hospital and they give you an IV, they're going to give you saline. It's physiological saline. It's going to have the same osmolarity as your red blood cell. It's going to be isotonic. That's going to make sure your blood cells stay happy and healthy and isn't going to stress them out. So this concept is very, very important. Make sure you know each one of these 3 solutions. Make sure you know if you are given a solution, whether it's iso, hyper, or hypotonic. And then further, make sure you know what happens to the red blood cell in each one of these cases so that you can predict, hey, if we put this red blood cell into this solution, what's going to happen? Okay. So go ahead and practice some of these with your homework. And it's a sort of a fun situation to go into trying to predict what's going to happen with that red blood cell.